So in this video I want to discuss the origins of the names of the trigonometric functions, why it is that we talk about cosines, cotangents, cosecants and so on. I still remember, for example, having explained to me by my teacher at school that the secant was 1 over the cosine and the cosecant was 1 over the sine, and just feeling somewhat confused by this. And also I'd like to try to explain why the tangent function, the tangent, say, of this angle, what that has to do with a tangent line to a curve. Okay, so to start with, very simply, when we think about a sine in a right angle triangle, you'd think of the sine as being defined as the opposite over the hypotenuse, and the cosine is the adjacent over the hypotenuse. But originally, a cosine was a cosine, like a co-pilot in an aircraft. So if we look at this other angle in our triangle, and if I'm using degrees, this is 90 minus theta. If I was using radians, it would be pi over 2 minus theta. Then the cosine of this angle was originally viewed as the sine of this angle. So the cosine of theta is the sine of 90 minus theta. So that means the sine of this angle is the opposite, which in terms of this angle is the adjacent, divided by the hypotenuse of the right angle triangle. So that is the adjacent over the hypotenuse. So a cosine was originally just the sine of the other angle. And in the same way, the cotangent would be the tangent of the other angle, and the cosecant is the secant of the other angle. So what we still have to talk about in this video is the idea of the tangent and of the secant, and the cotangent and the cosecant are then given to us for free. So let's move on and talk about the tangent. So let's consider here a line, and I'm going to say its length 1, and at the moment it's lying on this axis, but if I rotate it like this through an angle here, and then I could change the angle, I could rotate it out through a larger angle, keep doing this, and what happens if I draw it well, which I probably don't by hand, but if I do it properly, if the line has the same length, this is sweeping out an arc of a circle. So this is an arc of a circle. And there is an important point on this circle, and for any particular angle, which is I'm going to call P, and this is, say, for the angle here being theta. Now, this point, you could imagine that there are two interesting ways of thinking about the tangent related to this, and I'm going to talk about one of them much later in the video, or somewhat later, and the other one we're going to look at on the next slide. But this idea of an arc of a circle that our point will lie on, I'm going to say its length 1, so the radius of this circle is 1 as well. The angle is measured this way, and this is our point. We're now going to look at that on the next slide and try to see how this helps us to understand the origin of the tangent function. So here is a diagram drawn somewhat more nicely. So I've drawn here a circle. We have a point P, an angle theta measured this way. The length of the line here is chosen to be 1, so this is 1 as well. This is a right angle triangle. I've dropped here a line that's perpendicular to this axis. And the tangent that I'm going to think about is going to be this line here, this dashed line. And if I take the line going from the origin to P, and I just continue it as with this dotted line, then one way of defining the tangent function is to say that it is the length of this line of the tangent to the circle when the angle is 0, going up, and how long it is until you meet the extension of this line of angle theta. So if theta was 0, the tangent would be 0, and as you increase theta, it gets larger and larger, and as theta approaches 90, this length is going to diverge, which is exactly what you would expect from the tangent function. So the tangent can be thought of as being this length CQ, and we have here in our diagram two similar triangles. This triangle, ABP, and this triangle, ACQ. They're both right angle triangles. This angle is the same, so these angles must be the same. So we have two similar triangles. Now, if we say that the tangent is CQ, then that means it is CQ over 1, and the tangent is therefore this length over this, 1, because that's the length AC, and the tangent will therefore also be this over this. And in terms of our right angle triangle, that is just the opposite over the adjacent. And if you were to say that you have, for a right angle triangle, some arbitrary hypotenuse, that ratio would be the opposite over the adjacent. So this length of a line that's the tangent to the circle when the angle was 0, and where it is crossed by extending this line, that is the origin of the tangent. And I'll talk later in the video about a slightly different way of thinking about it, which gives us the same result and is also clearly in terms of a tangent. So what I want to talk about now is the secant function. And to understand that, it's useful to know that in Latin there is a verb secare, which means to cut or intersect. So if we take again our tangent line, and we have the line of angle theta, and now I'm not just dotting this, I'm just extending it straight out until it hits the tangent line, then this line crosses, intersects or cuts the circle here. And the length going from the origin all the way to where you hit the tangent line is the secant function. It is the length of the line that cuts or intersects the circle. So the radius of the circle, AC, is 1, and the secant is this length, AQ. So sec theta is AQ, that is AQ over 1, and by looking at the similar triangles, AQ over 1 is the same as this length over this length. So it is the hypotenuse divided by the adjacent. And the way I've drawn it here, this hypotenuse would be 1, but generally this idea leads to saying that the secant function is the hypotenuse over the adjacent. And then the hypotenuse over the adjacent, thinking that the sine is this over this, the cosine is the sine of this, the secant is 1 over the cosine. So in this way we see that the secant, this length, through thinking about similar triangles and starting off with this having length 1, gives us that the secant is 1 over the cosine. It is the reciprocal of the cosine function, and this idea of cutting is there. So now, having thought about tangent and secant, we get cosecant and cotangent for free. The cosecant, or cosec, is the secant of the other angle in a right angle triangle. So if we say that sec theta is this over this, then cosec of theta is going to be the secant of this angle, 90 minus theta. So it is going to be the hypotenuse divided by the adjacent to this angle, which is the opposite of this angle, so it's h over o. So secant is the cosine of this, or sorry, is the reciprocal of the cosine of this. The cosecant is the reciprocal of the cosine of this angle, but that means it's the reciprocal of the sine of this angle. And in a similar way, I think you should check that if the cotangent of theta is going to be the tangent of 90 minus theta, so looking at the other angle, then this tells you immediately that the cotangent of theta is the reciprocal of the tangent. Now, when we drew this diagram earlier on, you may have thought to yourself that there is another way of thinking about the tangent for this point P, which is determined by our angle theta. You could look at the tangent line at the point P. And you might say, well, the tangent, a natural way of defining it, could be the length from P to the point C where it crosses this axis. So if you were to say that this was the tangent and this length is 1, then in a similar way, using similar triangles, you can show that this length is equal to this divided by this. And therefore the tangent of theta with this definition also gives you that the tangent of theta is PB over AB. So it is the sine of theta over the cosine of theta. So that's, I think, worth checking. So to conclude the video, what I would like to point out is that this is history, and it tells us about the origin of the names, and I think it's interesting to know this, but the way I would think about trigonometric functions is to consider a unit circle centered at the origin and say that the coordinates of the point P, the x-coordinate is the cosine of theta and the y-coordinate of P is the sine of theta. I would then say that the tangent of theta is just defined as the sine over the cosine, the cotangent is the reciprocal of the tangent, 1 over the tangent. I would say that the secant is 1 over the cosine, just as my teacher said to me many years ago, and that the cosecant is 1 over the sine. But I think it's interesting to have heard a bit about the names and their origins, and I hope it makes it seem a little bit more natural to you. With that, I'll stop this video.